Hey guys, I know no one really cares, but I'm Jacob.
Nobody cares.
From Miss Collins' chemistry class. This is my end of the year project. I got 5 topics for you guys. Number 1 is Gay-Lussac's law.
Gay.
Anyways, look at this mac and cheese, guys. I got this from Chick-fil-A. This should be your reason to stop supporting them. They're homophobic, and their mac and cheese is dry as Can't say that because it's a school project. But I don't go to your school. I'm eating my mac and cheese, bro. Leave me alone.
Anyway, my 4 other topics. They're going to be about the states of matter, electrons and atoms, behavior of gases, and chemical reactions.
Chemical reactions.
All of these topics have been graciously sponsored by the chemistry department at MLK. And I want to give a big shout out to Miss Collins for helping me blow a bunch of stuff up in her laboratory.
And me, bruh. Hey, Jake, you know my Snapchat. Any cute girls in your class? Or guys. Screw it, right?
Don't do this stuff at home. Like, he's literally doing some Breaking Bad stuff. Wait, that's meth. Okay, never mind.
Alright, our first topic is chemical reactions. To demonstrate what I mean by this, I have some cotton balls, paper towels, some fire, and some isopropyl alcohol. I think you and I both know where this is going. Alright guys, before we start this chemical reaction, we need to find out what a chemical reaction is. So, a chemical reaction is a process that involves the rearrangement of the molecular/ionic structure of any substance, as opposed to a physical or nuclear reaction. With a physical reaction, you can change the new substance back into its original form. For instance, boiling water, you can always freeze it and change it into any shape you want. And with nuclear reactions, well, a nuclear reaction is considered to be the process in which 2 nuclei, or a nucleus and an external subatomic particle, collide to produce 1 or more new nucleides. AKA, you gotta get away from that stuff if you're dealing with that. Alright, let's just go on with the experiment. Let's light some stuff on fire. Alright, now that we got that out of the way, let's see what really happened. But first, we need to understand what we're actually dealing with, element-wise. When ethanol burns, it reacts with oxygen and produces water and carbon dioxide. The chemical equation of the combustion of ethanol is C2H5OH plus 3O2 will yield to 2CO2 plus 3H2O. The combustion of ethanol creates an exothermic reaction. What's that, you ask? Well, an exothermic reaction is a process in which a reaction lets off an excess amount of energy. And in this case, it's fire, as with most cases. And that's honestly pretty much it for chemical reactions. Let's move on to the next thing. Alright, this experiment is going to be about the behavior of gases. Some gases and fumes are much more flammable than others, which is always why you want to be careful around those guys. For example, water vapor will most likely expel a fire, while the fumes of gasoline will probably instigate a fire's growth. In this experiment, we will learn that isopropyl alcohol and ethanol have an extremely flammable fume. Actually, let's cut to that right now. Wait. Before you guys go, I want to tell you something. I'm going to be using 3 different solutions, one of which will be 95% ethanol, the second will be 91% isopropyl alcohol, the third and final one will be 70% alcohol. The difference between these are the rate at which they're going to flame and practically just light on fire, and 2, that's honestly pretty much it. Just thought I'd let you know, but the first video I want to show is going to be ethanol, which is going to be the most explosive. Second will be 91% isopropyl alcohol, which is going to be a little less tame, but, still pretty cool. And third will be 70% alcohol, the lame one, which is going to kind of suck. But you know what? We're going to make it work.
Yeah.
3, 2, 1.
Nice.
lot more lame.
Hopefully this will work. So yeah.
You ready?
Yep. Oof.
I think that was it.
I thought it would burn a lot slower. Alright, that was pretty cool. Let's talk about what happened. So, as we know, an exothermic reaction lets out a lot of energy. But where does that energy come from? Well, before the camera started rolling, I shook a jug for around 2 to 5 minutes. This creates something called kinetic energy, which comes from the rubbing against the alcohol in the jar. Kinetic energy is an energy, shocking, I know, which a body possesses by virtue of being in motion. The formula for kinetic energy is half the mass multiplied by the squared velocity. So if I were spinning a jug at, let's say, 5 meters per second, and the mass of the alcohol was around 2 kilograms, the kinetic energy would be 25 joules. Friction also comes to play, and that's what's created when the alcohol rubs against the jug. The formula for friction is the coefficient of friction multiplied the actual, the normal force. This is good to keep in mind during the experiment, but not necessary. Okay, I could go all day about talking about energy, but what does this actually have to do with gases and the behavior of them? Well, when the alcohol goes through kinetic energy, the fumes or gases are released and trapped due to the jug being closed. The more shaking, the more gas released. The 91% alcohol burns quite quick, as you saw, because there isn't a lot of other elements in the solution compared to the 70% alcohol. This is because 30% of the water vapor slowing down the burn, but only by a little bit. Now, the 95% ethanol was obviously the most aggressive and looked the coolest, because once it had started the percentage of straight up ethanol, there was no turning back. But also because ethanol's fumes are way more reactive than the other solutions. The fumes created during this experiment aren't harmful, but they'll set you on fire. I mean, they did me. And that's good for gases. But this experiment I call the whoosh bottle. Let's move on to the next thing, I guess. Alright, hey guys, it's Future Jake again. Forgot to add some stuff in the original video, so I'm going to cover some stuff. This is the start of Experiment 3, which covers the states of matter. And today we'll just be using the element water. H2O is our element of choice. But honestly, you can really use any element you want, considering everything has its own boiling point. For example, gold has a boiling point of 2,966 degrees Celsius, which might seem high, but compared to uranium, which is like 7,468 degrees Fahrenheit, there's obviously a huge difference. So, if you have some gold, some uranium, or even water lying around, feel free to follow these steps with me. It's not that hard. Now, as most people know, if you heat up water, it'll start to disappear. Let's cut straight to the reaction. Alright, what we have here is a pot of water at room temperature. Now let's see what happens when we heat it up to its boiling point, which is around 212 degrees Fahrenheit. Alright, so it's been about 10 minutes of this water boiling. Now let's see what's happened. It's a little hot. But as you can see, all this steam and water vapor that's come up is because the water has been heated up and is now boiling and is now expanding into a gas. And this is because when any element heats up, the state of matter it's in will change into a gas, from a liquid at least. Okay, that one was kind of boring too, but let's talk about what happened. So I took room temperature water and applied a heat source. Then its property changed. Why? Well, when any heat source is applied to an element, its property will change. With room temperature water, it only took a few minutes for the water's property to change from a liquid to a gas. This is because water's boiling point is only 212 degrees Fahrenheit, which is obviously a lot lower than both gold and uranium. But let's be honest, we probably don't have that just lying around. The way this happens is when an element is heated up, its particles will become more spread out and less compact. The heat will also change the particle's speed, making them go faster. All of this transforms a liquid into a gas. But when you freeze something, it's the exact opposite. When any element succumbs to cold temperature, its particles will decrease in speed and get closer together and more compact. This transforms any element into a solid. Water's freezing point is 32 degrees Fahrenheit or 0 degrees Celsius. And that's pretty much it for the states of matter. Right, onward to the next thing. All right, this is topic 4 of 5. I call this experiment the imploding can, for obvious reasons. Okay, so this topic will cover the basics of Gay-Lussac's law, which relates to pressure and temperature. Gay-Lussac's law is a gas law stating that the pressure and volume of gas have a direct relationship. As temperature increases, the pressure will increase at the same rate, and as temperature decreases, pressure will also decrease. Joseph Louis Gay-Lussac was a French chemist and physicist. He was born December 6, 1778, and died May 9, 1850. He is known mostly for his discovery that water is made of 2 parts hydrogen and 1 part oxygen, his 2 laws related to gases, and his work on alcohol-water mixtures, which led to the degrees Gay-Lussac used to measure alcoholic beverages in different countries. Interesting. Wait, back to his gas law. The equation for the law is pressure 1 divided by temperature 1 will equal pressure 2 divided by temperature 2. In this experiment, I'll explain how Gay-Lussac's law can be applied to any object in the world, or screw it, the universe. All right, let's just see it in action.
No, I mean, if you know what it is, my thing is, as long as you know what it is, and when it's time for you to speak, there you go. You have a few different, you have the high score list, you have high list.
All right, that was pretty cool, but let's see what actually happened. So, the can was heated to its water boiling point, which we know is around 212 degrees Fahrenheit or 100 degrees Celsius. And once the can is heated, I put it upside down in cold water. This will dramatically drop the can's temperature, will also drop its pressure, causing an implosion. And honestly, it's as easy as that. Gay-Lussac's law wrapped up in a minute or two. Well, on to the last thing, I guess. All right, we're almost at the end, but we still have one more topic, and that is electrons and atoms. Electrons, what are they? They're negatively charged particles that rotate the nucleus of an atom. They act as the primary carrier of electricity in solids. When electrons are added to an atom, the increased negative charge puts stress on the electrons that are already there, causing energy to be released. This explains every type of energy ever, from fire, which we've been using a lot of, to nuclear bombs. When electrons are removed from an atom, that process requires energy to pull the electron away from the nucleus. Addition of an electron releases from the process. In this lecture, you'll see how electrons can get excited around released electrons. Actually, let's see it happen, but let's make it a little more colorful.
Uh-oh, we gotta do that again. I jumped.
No.
Oh, man.
Wow.
That might be too strong. Hold on, because that might crack. Hold on. Okay, wait a minute. Maybe the acid is a little bit stronger than it should be. Try it again. We'll see.
All right.
Maybe we should have did this in the fume hood.
There we go.
Wow, that's pretty cool, though.
That's really cool.
There we go.
That's a little tamer.
All right, I think we're good, because that's scary.
All right. That should be good.
Yeah. Boom, there we go. Swirl, swirl, swirl. It ain't reacting. It is. Oh, yeah, it is. See it?
There we
There you
go.
go.
That's
There
what
we
we want.
go.
That's what we want.
Now it's smoking. Now, let's see if we get the blue fire. Now, hold on. I'm going
Step
to come back here this time. You know how I am, Turner.
All right.
Mm-hmm.
Whoa, like the aluminum jump.
Swirl it, swirl it.
That aluminum is almost gone. That's crazy.
Now, yeah, it's reacting. It's bubbling. Woo!
Wow, that was
We're gonna-
loud.
All right, we're going to let that be.
Oh my.
Man, the aluminum shot out of there.
Wow.
That was a little dangerous.
How was it a little dangerous? It's a good thing I was back. It was great that I caught that on video. Alright, that last experiment was dope. I definitely saved the best for last. But there is a lot to digest. First, I put copper 2 chloride in a flask with 15% hydrogen chloride solution, which is actually 12 molars. You might have seen the solution turn green. This is because when copper 2 chloride and hydrogen chloride mix, it creates a chemical reaction that forms the element cupric chloride. A rolled aluminum foil is then placed in the solution. The surface aluminum oxide reacts with the hydrogen chloride. Then aluminum reacts with HCl and releases H2. Energy from H2 combustion excites the copper electrons. This creates the energy for the blue fire. You might have heard the popping sounds in this video, but maybe not. It's fine. In this reaction, the H2 is reacting with the surface oxide. That's what the popping sound is. And obviously, this is normal for any H2 combustion reaction. The fizzing sounds is from the H2 bubble production. In conclusion, the electrons from atoms can create immense amounts of energy and sometimes creative reactions. Alright guys, Future Jake again. I hope you enjoyed the video. It's been a lot of good time and effort into it. We've been over 5 topics in total, and to wrap it up, these topics have been the behavior of gases, electrons and atoms, states of matter, chemical reactions, and Gay-Lussac's law. These topics all relate to one another in some way, shape, or form. But chemistry is a wonderful subject to learn, and you can do a lot of fun stuff with it. You just have to really know what you're doing. And by all means, you can really try all these experiments at home. Just be careful with the fires and the alcohols and the acids and whatever might kill you. Well, that's it. Stay in school, don't do drugs, and Miss Collins is the best.
Thanks for watching, guys. It means a lot. Shout out to Miss Collins. Right? That's what you say, right? Dude, you have ice cream all over your arm. You've had it on there this whole time, but I wasn't gonna tell you because I thought it was funny. Miss Collins, I don't know you, but you're the G. Cause is she cool, right?
She's cool.
You're cool.
Oh, it's green.
Yeah. That's good stuff, huh?
Again, guys. He's like a really smart dude. Like, I hope you enjoy. He's kind of smart.
Yeah, because no one's as smart as this guy.
He's almost smart. That was very passive aggressive. Like, I'm